Number 30. Sources of the magnetic field. In the previous chapter, we introduced the concept of the magnetic field, and we focused our attention on the magnetic field exerting a magnetic force on a moving charge or a current. And we look at various examples of the magnetic force. But in this chapter, we're going to ask the following question. What causes a magnetic field, and how does it do that? Well, actually, we know from the previous chapter, from the Oster's experiment, we know that it is an electrical current or a moving electrical charge that can cause a magnetic field. But we didn't address how this is done. What kind of, given a current or given a charged particle, what kind of field, what kind of magnetic field can it produce? Okay, and this is the question answered in this chapter. So, electrical current causing a magnetic field, but exactly how does it do that? Well, we can focus on a single moving charge, or we can focus on a segment of current. Each single moving charge in a segment of current will produce its own magnetic field. So if you look at an infinitely long segment, there will be an infinite number of charge carriers, each producing a magnetic field that could lead to an infinite large B field. So what we're going to do is we're going to isolate a small segment, okay, an infinitesimal small segment of the current out, and look at how this small segment can produce a magnetic field. And later on, if you want to know the magnetic field at this point coming from all segments of the current, all you have to do is to add the contributions up by the superposition principle. So we're going to isolate this little current element. It is analogous to a single point charge in producing an electric field. We want to know, how does this element of current produce a magnetic field at a point P? Okay. Now, in the case of the electric field, the source was just a point charge. Okay, and all we have to know is where it is and the charge, the amount of charge Q, which is a scalar. But this time we have a current element. Not only do we have to know where it is, in other words, we want to know the vector displacement between the source and the point of interest. We also have to know the orientation, right? The orientation of this element, because it makes a difference whether the current flows in one way or in another way. So we have here a vector ds, which is the displacement vector from the beginning of the element to the end of the element. Okay, a current flows along ds, so ds is along the direction of current flow. And we want to know, what is the magnetic field P at point P? This magnetic field is infinitesimally small, but because it is produced by infinitesimally small segment, so we're looking for dB basically. Okay, looking for dB. What is dB equal to? Well, dB is a vector which depends on two other vectors. One is ds, the other is r. And we have seen something like that before in a previous chapter, right? The magnetic force exerted on a moving charge was a function of two other vectors. One was v, the velocity of the moving charge, and the other was b, the magnetic field, right? And we argued by symmetry at that time that the resultant vector f, the magnetic force, has to be perpendicular to what? To both v and b, okay? To both these vectors. Now in our case, we have a magnetic field dB, which depends on two vectors ds and r. Can we make a similar argument to indicate the direction of dB? Well, it turns out, yes, we can do that. And the argument is totally analogous to that we did in the previous chapter. Basically, reverse both ds and r and see what happens. And that is equivalent to rotating the whole thing by 180 degrees and so on and so forth. And you can do that argument yourself, and you'll find that because of symmetry, the magnetic field at point P, okay, has to be perpendicular to both vectors ds and r. In other words, it will be in the direction of ds cross r, or r cross ds. Which one do we pick? That is entirely due to convention. Okay, it's how we define the magnetic field, positive direction of the magnetic field. So it is not a surprise to see that dB is proportional to ds cross the unit vector r. That as far as the direction is concerned. Okay. Now, also, it is easy to understand that the magnetic field should be proportional to the current Because if I double the current, then I have twice as many moving charges here. Each can produce a certain amount of magnetic field here, so the value of dB will be doubled. So it is proportional to I. Okay. Now, another thing is, how does it depend on the distance? How does it depend on that distance? Well, in the case of Gauss's law, we know it was an inverse square law, the Coulomb law, that makes Gauss's law unique, right? So in the case of electric field produced by point charge, you know, the field goes down by 1 over r squared, the famous inverse square law. Do we have the same situation here? Well, electricity and magnetism, they go hand in hand. So it is still quite easy to understand, at least qualitatively, that we have the same inverse square law here for the magnetic field as well. Okay, it also goes like 1 over r squared. So it goes like 1 over r squared. See, we didn't derive this, okay, but we just try to make it sound plausible. That's all. So it turns out dB is proportional to I ds cross r over r squared, and this r, as you see from with this cap, it is only the unit vector has the magnitude of 1. Okay, so it goes like 1 over r squared as far as distance is concerned. To make it equal, we have to introduce a constant, okay, k. And that k has to do with magnetism, not electricity, so we use a subscript m to indicate this has to do with the magnetic field. That completes the expression for dB, okay? And this expression tells us how to find the magnetic field of a current element. It is analogous to the Coulomb's law, which tells you how to find the electric field produced by a point charge. Okay, so we use a current element to replace an electric charge in producing the magnetic field. And here this Km is equal to 10 to the exactly equal to 10 to the negative 7 Tesla times meter over M. First of all, the units are quite straightforward to understand because basically you have to balance the units of both sides. This is Tesla, and here is there's a meter squared, so overall there's a meter going over, and then I, which is an amp, goes down like that. Okay. Now, why is it exactly equal to 10 to the negative 7? No more, no less. Well, it's because how we define Tesla. Okay, Tesla is a new unit, and the way we define Tesla, okay, is based on the choice of this constant k. So we can choose the constant k to be any value we want. We can even choose it to be 1, but that was not the convention people adopted. And just like the case where in the Coulomb's law you have Ke, which is defined also as 1 over 4 pi epsilon naught, remember that? Okay, here we also define Km as another constant mu naught over 4 pi. Mu naught over 4 pi. And that mu naught, of course, then becomes 4 pi times the negative 7 in SI units, and it is called the permeability of free space. So there is a fundamental constant here, mu naught. Given that, we can find Km. Okay, so we have two fundamental constants we learned so far in Physics 1c. One was epsilon naught, that is for electric field, and the other one is for mu naught, that is for the magnetic field. Okay, we'll come back to these two constants later and we'll see how we can combine them to do something magical. But let's go back to this formula. This is, again, analogous to Coulomb's law. It has the same importance in the calculation of magnetic field as Coulomb's law is to the case of electric field. It is called the Biot-Savart law. Okay, the Biot-Savart law. And again, the electrical charge in the case of Coulomb's law is now replaced with a current element. Okay, now, this is only the electric magnetic field produced by a current element. What if you have a finite length segment? Okay, say from here to there. What is the total magnetic field produced by this entire segment? Well, remember how we went from a single point charge to a bunch of charges to any charge distribution? Okay, the key was to use the so-called linear superposition principle, right? It turns out the same superposition principle applies here in the case of the magnetic field, which means if you have a whole bunch of current elements, not just one, okay, then the superposition principle says that you can calculate dB created by each element as if the other segments do not exist, right? Just like this. And then all you have to do is to add them up linearly. Just dB1 plus dB2 plus dB3 and so on. You'll get a total magnetic field. So, again, the same superposition principle, linear superposition principle applies to the B field, not just the E field. In other words, B of a finite current distribution is just the sum over dB. Okay, just a sum over dB. You just sum over the contribution from every current element of the entire source. That is how you go from current element to any current distribution.